Hi everybody, it's Cameron here. Today we're going to be looking a bit more in detail into unbalanced forces. I know we touched on it a bit, I think 2 videos ago, but that's just what these books are like. It's quite strange. But anyway, we're going to be looking this time at momentum elasticity in a bit more detail. Okay. So as we mentioned last time, Newton's second law of motion is that dealing with unbalanced forces. Okay, so our force is directly proportional to our acceleration and vice versa, and our acceleration and our mass are inversely proportional to one another. So as mass increases, the acceleration is going to decrease. As our force increases, our acceleration is going to increase. Okay, so let's look at forces and braking. So a driving force is something that is making the object move. Okay. So at terminal velocity, the driving force is equal to the air resistance. Now, terminal velocity is when an object starts to fall, it'll reach a point where it is not going to accelerate anymore. It's going to be falling at a constant speed because the driving force, that's weight, okay, gravity pulling it down, is going to be equal to the air resistance pushing it back upwards. Okay. Now the braking force in this point would be something like the air resistance, but for a vehicle to stop in a given distance is the braking force. Okay. Now it depends on the mass of the vehicle. So something like a truck would require a lot more braking force than something like a car. Okay, as well as the speed of the car when the brake is applied. Obviously, right? If it is going fast down a hill or it is going up a mountain, the braking force is going to be different for both. Now, the greater the velocity and the mass, the greater the deceleration required to stop that object or that vehicle, and the higher force is required. Okay, so the brakes on a truck are a lot stronger and a lot bigger than the brakes on a car, for instance, okay, due to its mass, due to the speed that it would go and the force required to stop it. Okay, now stopping distance is a bit different. Stopping distance relies on the thinking distance, okay, so the reaction time of the driver to start braking and the braking distance. So once the person has started braking, how long will it actually take for them to stop? Because remember, cars can skid. Okay, so even if you put brakes, you're not going to just stop right where you are. There's going to be a distance that you'll travel. Okay, and this is why it's so important when you're driving to have safe following distance, as well as not being incapacitated in any way. So if you are tired, if people are drinking alcohol while they're driving, or if they have drunk alcohol, this can increase their thinking distance. Okay, so they will take a lot longer to realize they need a break. Okay, and then the braking distance will remain the same, I guess, but it's that thinking distance that needs to be very quick. Okay, so stopping distance equals thinking distance plus the braking distance. So how do we calculate this braking force? Okay, so we're going to use the calculation force equals mass times acceleration. Okay, but first let's look at this example. So a 1,000 kilogram car traveling at 10 meters per second needs to stop at a traffic light in 20 seconds. To stop means to come to a velocity of 0. It is currently going at 10 meters per second. So we can calculate the acceleration that needs to happen in this time, or the deacceleration rather. Acceleration equals to the change in velocity divided by time. The time we know is 20 seconds. The change in velocity is going to be your final velocity minus your initial velocity. Final is 0 minus 10. That will give us 0.5 meters per second squared, or negative 0.5 meters per second squared. So that's the deacceleration. Okay, they're asking here, calculate the braking force required. So force equals ma, that equals to 1,000 multiplied by negative 0.5. So we need a force of negative 500 newtons, okay, to stop this car. So apply the force in the opposite direction of the motion. Okay, I think the negative will suffice for that. but you can also just say 500 newtons in the opposite direction of the car. Okay. So we talked about momentum in the other lesson as well. Momentum is going to be a vector quantity dependent on the mass and the velocity of an object. Okay, so mass multiplied by velocity is equal to momentum. So if something undergoes a change in momentum, we call it an impulse. Okay, impulse can also equal to force multiplied by time. So if we extend the time that an impulse occurs, it is going to lessen the force. So why do I say this again? Because we have something called the law of conservation of momentum. Okay, so this states that the total momentum before a collision is the same as the total momentum after the collision. Okay, in a closed system. So that momentum had to go somewhere. It's going to be transferred between objects or between the ground and the environment. Okay, so if we look at elastic collisions, okay, elastic collisions are when objects collide and bounce off one another. The momentum and kinetic energy are conserved within the system, always. Okay, so as they come together, their momentum, their total momentum off before they hit and after the collision is going to be the same. Okay, just in opposite directions, I guess, for each one, but in total, they are the same. Inelastic collisions are when they collide and they stick together. Okay, now you might, so momentum, but not kinetic energy is conserved in this case. Okay, and you may, well, how is it possible that their momentum, let's say two things are going to be coming at each other, okay, and once they move afterwards, they might be moving a bit slower in one direction, okay? Their momentum is conserved because we take their total mass right now. The total mass has increased, okay? And therefore, even if they're moving slower, their momentum is going to be the same. So initial momentum is going to equal final momentum, and you can use this calculation over here, this formula for mass and velocity, to calculate, let's say, the final velocity or the final mass, saying that the initial equals the final for momentum. Okay, so you would say mass multiplied by velocity is going to equal to mass multiplied by velocity. You know what I mean. Okay, and finally we're talking about elasticity. So an object is elastic if it can return to its original shape after a force is applied to it. So this can be an elastic band, like a rubber band. It can also be a ball, like a sports ball, bows, so bow and arrow, example of elastic, and springs. Okay, so the extension of the spring is directly proportional to the force applied to it. Okay, so how that works is the spring is going to be changing distance. That's what it is. Okay, it's either going to be compressed or it's going to be pulled apart, and then it's going to go back to its normal size. Okay, now depending on how much force is applied to it, it is then going to have an increased extension. Okay, and depending if the extension is increased, it's going to have an increased force that it will now exert outwards when it returns back to its normal shape. Okay, the spring constant, okay, K, is going to be a constant value for a specific material. Okay, so a metal spring and a plastic spring are going to have different spring constants due to the material they're made up of. Okay. So, my name's Cameron, and I'll see you in the next lesson.